Hello, we're going to be doing chapter number 4. Just as we complete chapter number 3, balancing chemical equations, both chapter 3 and 4 are become correlated to one another. In order to make sure that you understand what we're about to do, let me open up my PowerPoint and share with you so that we can go quickly over it. I may not do all of it, but at least part of it to get you the idea. And with that, I'm going to start what the content for at least the first section deals with. Stoichiometry means mass relationships in chemical reactions. And when we talk of mass relationships, we are basically talking about interpreting the balance equation in terms of moles. This means we must know how to determine the amount of reactant used, needed, or produced, or obtained. And then finally, we try to understand what the terms limiting reagent, theoretical yield, and percent yield. So let's go to the brief summary first. The stoichiometry provides a relationship between the amounts of reactants and products formed. And this particular concept is based on the law of conservation of matter, which states that matter can neither be created nor destroyed in a chemical reaction. That means the matter must be conserved in a chemical reaction. What does it mean? It means that the number of atoms on the reactant sides, the total mass, must equal the number of atoms on the product side and their mass. The stoichiometric balancing coefficients for each of the reactant compounds or the products are the numbers in front of a balanced chemical equation, in front of the formula in a balanced chemical equation. So the ratio gives us the conversion factors that we need when going from A to B. The coefficient allows us to literally determine how much amount of a reactant we need and how much product we would get or supposed to get. Sometimes when we do experiments, we do not get what we are supposed to get. And therefore, it gives us a means of how to do it. For example, this is a problem, stoichiometric example, which I'm going to discuss. So 2 moles of C2H6 plus 7 moles of oxygen gives us 4 moles of carbon dioxide plus 6 moles of water. Now, the numbers 2, 7, 4, 6 in front of each of the reactants and products literally give you the moles that is required or you should get. So now, what does this mean? This means that if you take 2 moles of C2H6, then you will need 7 moles of oxygen. And when you burn that with 7 moles of oxygen, you would get 4 moles of carbon dioxide and 6 moles of water. And the question asked is, how many moles of water are produced when 3 moles of oxygen react? So the solution is, what do we see from the equation? We see that 7 moles of oxygen will give us 6 moles of water. But how many moles of oxygen do we have? We have 3 moles of oxygen. So 3 moles multiplied by 6 moles of water divided by 7 moles of oxygen will give you 2.6 moles of water. Now, this mole of water, because it is also in mass, we can convert it. So all you have to know is that in 1 mole of water, there is 18.02 grams of water. So to get it in grams, all you have to do is multiply 2.6 times 18.02 grams of water, and you get your answer in mass. Another example. So And these are some reactions that you can do for practice. So iodine and fluorine combine, react to form iodine trifluoride. So you get I2 plus F2 gives you IF3. First thing we have to do is make sure we balance the equation. Then once you balance it, you get a stoichiometric equivalence. And so in this case, we see that we have 2 moles. So we see that if you have 1 mole of iodine plus 3 moles of fluorine will give us 2 moles of IF3. This is a balanced equation because on the left side you have 2 atoms of iodine. On the right-hand side you have 2 atoms of iodine. Right-hand side 6 atoms of fluorine. Left side 6 atoms of fluorine. And therefore you get your balanced equation. Now, when we have this equation set up, then we know the conversion factor. So we see that for 1 mole of iodine requires 3 moles of fluorine, or 3 moles of fluorine will require 1 mole of iodine, etc. And so you can correlate each of these mole equivalents. Therefore, if we say that for 2 moles of IF3, you will require 3 moles of F2. And if you have 2 moles of IF3, then you need 1 mole of iodine isotopes that are there. So a molecule I2 of iodine. And therefore, you can see how the mole coefficient calculations help us to determine what we need and how much we need. Now, generally speaking, we cannot do any stoichiometric problem calculations without balancing a chemical equation. Why? Because chemical equation, once they are balanced in terms of mass and moles. And therefore, whenever you get a grams of any substance, you convert it to moles by using the molar mass. So grams of a substance divided by its molar mass will give you the moles of that particular substance. Then if you want to go from mole of one reactant to the mole of the second reactant, then you can multiply that by the mole ratio. What is the relationship between the 2 moles that you are looking at? Once you get to the new mole, then you multiply it by its molar mass to give you the grams that is required. The same thing is given in the chart as shown. Remember, you cannot go to gram A of a reactant to gram B of a product. You have to take a longer way because we have to use the mass-mole relationship in order to get a balanced equation. So in one type of equation here, you have to, in mass, so we have the reaction CH4, that's the methane gas, requires 2 moles of oxygen to give you 1 mole of carbon dioxide and 2 moles of water. One thing you have to remember in such kind of compounds which have only carbon and hydrogen, that the final product will be carbon dioxide and water. The number of carbon dioxide produced will depend upon the number of carbon atoms that is present in the molecule, and the number of water molecules produced will be exactly half the number of atoms in the original compound that is there. And so now we have, using the same relationship in the problem, they say you are given 8.32 grams of methane, and you want to know how many grams of oxygen is used and how much of carbon dioxide and water is formed. And so you can see, convert the grams of methane to moles of methane. Then convert the moles of methane to moles of oxygen. Convert the moles of oxygen to grams of O2. And that is how you do your calculation for oxygen. In the same way, try to do that for your carbon dioxide and water. So now here's a self-help question. You can answer it. Same thing. Now, Once we know exactly what the mole relationship is, then it is always easy to solve reactions involving a limiting reagent. First thing, what is the meaning of limiting reagent? Limiting reagent or a reactant is one that is completely used up in a reaction. So if you remember that, then it is very easy to go forward, because the limiting reagent, that reagent which is completely consumed during a chemical reaction, will limit the amount of product that you can get. And therefore, we see that the maximum amount of product that you can get or obtain from a reaction is equal to the moles of the limiting reactant that is there. And this can be equated to nuts and bolts. So if you can go through this analogy to help you understand what we are trying to do. And this is another stoichiometric calculation using a limited reactant that is there. So, and here, this is the manufacture of nitric acid, which is the process of oxidation of ammonia to NO, nitric oxide. So 4 moles of ammonia reacts with 5 moles of oxygen to give you 4 moles of nitrogen, nitric oxide, and 6 moles of water. And then, of course, the problem extends and you can read it and solve it. So the steps are the same. Calculate the amount, moles of each reactant, calculate the mass of the product, determine the limiting reagent, and the maximum mass of product that can be obtained. So when we say the maximum amount of product that can be obtained in the reaction, first thing, in order to determine the limiting reagent, for each reagent, see what is the maximum amount product. If that particular reagent was completely used up, get the maximum amount of product that would be obtained. Then select the product, the maximum product, which is of a lower value, and on the left-hand side, you'll get your limiting reagent. And after that, you can calculate how much of the excess reagent was left behind. And here, the steps are involved. How they are done is shown to you. Now, I'm going to stop this because at the bottom of these slides, you will find self-study questions which will help you to understand the principle behind what you are doing.